Let's solve problem number 15 from LeetCode, which is called 3-sum, and it's rated as a medium difficulty. Hey everyone, welcome back to the channel. This is Keystrokes. Today we'll look how to solve problem number 15 on LeetCode, which has been an interview question for Apple, Amazon, Google, Microsoft, and so many other companies. We'll start with a brute force solution, and then we'll figure out an optimal solution for it. And on that note, here's my interview tip. Whenever you are given a problem, always think aloud. And it doesn't hurt to mention the brute force solution. Just make sure that you call it out that it's brute force, and then we need to find a better solution to it. That way, the interviewer knows that you've already thought through the brute force solution, and that helps the interviewer understand that you understood the problem well, and now you're thinking on how to optimize it further. Okay, so let's take a look at the problem statement. We are given an array of integers, and these integers could be positive or negative or 0, and our goal is to return all unique triplets that add up to 0. And for each unique triplet, an index can be used only once. So let's look at example 1. Here we have the nums array. It has a bunch of numbers, and you can see that the output has 2 triplets in here, and they all add up to 0. In the explanation, it says you can actually have 3 triplets at index 0, 1, 2, 1, 2, 4, and 0, 3, 4. But the first 2 triplets are the same, which is -1, 0, 1, and you can see it's the same here, -1, 0, and 1. And then the third triplet is a unique one, which is -1, 2, and -1. So that's why we get only 2 triplets from this. Next, in example 2, we have 0, 1, 1 as the input integer. And because it's only 3 numbers, that's the only triplet that's possible here, and we can see it doesn't add up to 0. And so you just return an empty array. In the third example, all the numbers are the same, which are 0, and when you add them all up, they sum up to 0. So that's the only unique triplet that you have in here. We have some constraints as well, but I don't think that it will affect our solution. Next, let's see what concepts do you need to know to solve this problem. The first one is loops. Because you're given an input array, we need to have a loop to iterate through it. Then as for data structures, we need to know lists and sets. We'll use list as a return data type, so you just need to know the basics of it. And we'll use sets to maintain unique set of triplets. And I forgot to mention, you also need to know the basics of arrays. And in this case, it's how to access an array element. Okay, so let's discuss how we can solve this through brute force. And as I always say, with the same force, don't forget to hit subscribe and like this video if this helps you. Okay, so let's say this was our input array. And what we are trying to do is find 3 elements that will add up to 0. So if we had to brute force on this, we will need 1 loop for each element. That is, in this case, we'll need 3 loops in total. So let's say our first loop is represented by this green arrow. Then our second loop by this blue arrow, and the third one by this orange arrow. So we initialize everything at the first element. Now, one of the constraints of the problem was that each index can be used only once. And in this case, all 3 loops point to the same index. So we can't really use this number at all. So let's move our third loop, which is pointed by the orange arrow, and go to the next number, which is 0. Now in this case again, the index pointed by green and blue pointers are the same, so we can't do anything about it. So we really can't use this triplet even if these add up to 0. And if you think about it, the first iteration by loop 3 will be totally unusable. So it keeps progressing forward, but because the green and the blue arrows, they point to the same index, we can't make use of any of these triplets. So after the third loop is done once, we move the second loop to the next element, which then points to 0. And we also reset our third loop to start from the first element again. Now this is again not useful to us because the first and the third loop point to the same index again. So we increment the third loop by 1. Now again, we cannot use this because now loop 2 and loop 3 point to the same index. Let's increment the third loop again and go to the next number, which is 1. Now the first loop points at -1, second loop at 0, and the third loop as 1. And all of these indexes are different. And when you add these numbers up, they do result in 0. So -1, 0, and 1 become one of our triplet candidates, which add up to 0. Okay, so continuing on with our third loop, now this moves to the next element, which is 2. Now -1, 0, and 2 do not add up to 0. So we keep moving. Now it points to -1. Again, this doesn't add up to 0, so we skip it. and then we move to -4, which clearly doesn't add up to 0. So this finishes another round of iteration for us. Now we'll move the second loop to the next index, which is 1, and then reset loop 3 to the first index. Now loop 1 and loop 3 point to the same index, so we cannot use this triplet. So we move the third loop to the next index. Now the three numbers, -1, 0, and 1, do add up to 0, and this becomes our triplet that we consider. So -1 is pointed by the first loop, 1 is pointed by the second loop, and 0 is pointed by the third loop. Continuing on with the third loop, now we move to the next element. Now because loop 2 and loop 3 point to the same index, we can't use this triplet. So skipping this and moving on to the next element for loop 3. Now it's -1, 1, and 2, which do not add up to 0. So we skip this and again move on to the next index for loop 3, which is now -1. Now this again doesn't add up to 0. So moving on to -4, and this one doesn't add up to 0 either. And so now you get the idea. We move loop 2 to the next index, then we'll run through loop 3 again, and we'll keep doing this until loop 2 reaches the end. And once that happens, we move loop 1 to the next index, and then we restart this whole process again for loop 3, for loop 2, and loop 3. And we just keep brute forcing all the triplets that we can find. And I think the one other triplet that will come out of this will be -1, 2, and -1, and they all add up to 0. But we can see the only two unique triplets in this case is this -1, 2, and -1, and -1, 0, and 1, because these two triplets are identical. So in the end, our answer becomes -1, 0, 1, and -1, 2, and -1. And this is what we return as our output. Okay, so here's the pseudocode for our brute force solution that we just discussed. We take nums as the input, and then we start 3 loops, all starting from 0 all the way to the length of the nums input. Now if all the indexes are unique, then we check if the values pointed by those indexes add up to 0. If they do, then this is the triplet that we want, and we can add them to our list uniquely. And after all the 3 loops are done, we just return all the unique triplets that we found. Okay, so let's code out this brute force algorithm. Okay, so here I have IntelliJ, and I've bootstrapped a main class and a solution just like we see on LeetCode, and I have some test cases right here. Our focus will be on the solution class, which takes in an integer array called nums as input, and it returns a list of integers as the output. And this follows the same signature as the LeetCode right here. So let's work on our brute force solution. As we discussed, we'll need 3 loops in here. So let me start writing our 3 loops. We can do the classic loop I, which will go from 0 all the way to nums.length, and then we'll do I++, and then we'll run 3 more loops. We'll change this to j, and maybe for a third loop we can call it k. Then our first condition will be to make sure I is not equal to j, and j is not equal to k, and k is not equal to I. That is, all 3 indexes are different. And if they are, then we have another condition to check if they add up to 0, which will be nums accessing the first element, then the second element, and then the third element. And if they add up to 0, then this is one of our answers. So let's create a list out of them. This will be, let's call it list, and we can do arrays as list, and we put all our 3 numbers in there. And I'm just going to copy paste. This is I, and then j, and then k. And to store our results, maybe we can create a set just so that we have a unique triplets every time. And let's call it result, and let's create a new hash set out of it. And then we'll add this list of triplets that we just created to our set. And we add them in there. And that should be it really, at least for the algorithm. Now we have to return this result. Now because it requires a list of lists, we can just create a new array list from our result, and that should do it. Let's try to run this program and see if it works. Well, it looks like we return a bunch of same triplets multiple times, and probably that's because we didn't sort it. So let's maybe do that. we can do collections.sort list. Let's try to run this again. And we see it's successful answer. So I'm guessing that every time we add a new list in there, the order of the elements matter, and that's how set determines if it's unique or not. So sorting it just helps to keep them unique. Now we can further optimize this. We start our internal loops every time from 0, which we don't have to really, because we should always work on elements that are ahead of the previous loop. So let's say for j, we can actually start from I plus 1, and for k, we can do j plus 1. Now there's one more small optimization that we can do here, and that's the upper bound of our loops here. So I is going all the way towards the end of the loop, j is going towards the end, and so is k, but we don't have to do that. Only k has to go towards the end. J can be at the second to last element because k starts from the next element after j, and I can be at second to last element because j and k will cover the last two elements. So this is just a small optimization, and I think we'll still get the right answer. Okay, this works. So let's copy this and try this out on LeetCode. So going to LeetCode right here, pasting it in, and running the test case. It's accepted, and now let's actually submit the solution and see how it behaves. I hope you weren't expecting anything else other than time limit exceeded, because this is brute force and it's very, very slow. Well, let's see how we can optimize this. So that was fairly easy, and LeetCode didn't really like that solution. So let's figure out an optimal solution to this problem. And one way you can help me optimize the YouTube algorithm is by subscribing and liking this video, and also by buying me some coffee. Okay, so let's start the brainstorming. Now let's see if there's a more optimal solution to this. So taking the previous input again, and if we think about our goal, we need to find all triplets that add up to 0. And those triplets have to be unique, and the same index cannot be used multiple times. So for a given number, let's say -1, such that it can add up to 0. But we can simplify this problem. So let's say we pick one number, which is -1 in this case, and we have to find two more numbers. We can reduce this problem to the two-sum problem that you solved before. And in this case, we want these two numbers to add up to 1. But in the two-sum problem that we have seen, we had to return the indices of the numbers. But in this case, we need to return the numbers themselves. So the first thing that comes to mind is to sort this list so that we can realize when we can do an early return from our loops. So if we sort this list, we end up with -1, -1, 0, 1, 2, and 4. Actually, this is supposed to be -4. So let me fix this up really quick. So it becomes -4, -1, -1, 0, 1, and 2. So let's see. So we'll run a loop from the first index all the way to the end. So let's start with -4, which is our first number in the array. And because we cannot reuse the same index again, we can initialize one pointer, which is right after our current number, in this case, which will be -1. Now -4 and -1 add up to -5, and we need to find 5 in this array, which will then add up to 0, and it will become our triplet. Now because this array is now sorted, we can start looking for 5 from the end of the array. So in this case, we can initialize another pointer which starts from the end of the array, in this case, which will be 2. Now if we add these three numbers, it will be -4, -1, and 2, which will give us -3. Now because -3 is less than 0, then it indicates that we need a larger number such that the sum balances out to be 0. And the way we can do that is by moving this pointer, which we can call as the left pointer, to the next number. Because as we move the left pointer towards right, the numbers get larger. And because our sum is less than 0, we can hope that we'll find an element which will then add up to 0. In this case, we encounter a -1 again, which does not add up to 0. So this is not our triplet again. So summing it all again, it's -4, -1, and 2, which again still gives us -3. So we move our left pointer forward again, and this time we point to 0. Now adding them up, it's -4, 0, and 2, which gives us -2, which is again not 0, but you can see how the sum is getting closer to 0. So in this case, we'll move our left pointer forward again, and now you point at 1. Well, adding it again, it's -4, 1, and 2, which adds up to -1, just one step away from 0, but still it doesn't add up to 0. Now because -1 is less than 0, we again move our left pointer forward, and point at 2. But now our left pointer and right pointer, they both point at the same index, and we know we cannot use the same index again. So we can't use this triplet at all. So now we reset everything and move our iteration to -1. We couldn't find any triplet that involved -4 such that it adds up to 0. So moving on to -1 now, we reinitialize our left and right pointers. The left pointer will point to the next element from -1, which will be -1 again, and then the right pointer will point to the last element in the array, which will be 2. Now adding all of these up, we have -1, -1, and 2, which gives us 0. So that's our answer. It's one of our triplets that we want. So what do we do now? Can we expect that there will be more pairs for this -1 such that it adds up to 0? We can clearly see that it's possible because we have 0 and 1 right here, which do add up to 0 combined with -1. So let's think what we can do with our left and the right pointers. We can either only move one pointer. Let's say we move left pointer to point to 0. Now I don't think that will help us because then we'll have 3 numbers, which is -1, 0, and 2, and we can see we get -1 and 2 the same. But for a given pair -1 and 2, there's only one way that it can add up to 0, which is by encountering another -1. But if we do encounter another -1, then we get the same triplet that we have found before, so it's not a unique triplet again. And the same story follows with moving the right pointer. If we keep our left pointer constant and move our right pointer by 1, such that it points to 1 now, such that it points to a previous element, then we'll have -1, -1, and 1. But again, we get -1 and -1 as the same. So the only way it can result in a 0 is if we encounter a 2. And if we encounter a 2, it again comes up with the same triplet, which is not unique because we have already seen that triplet again. So it might make sense to move both the pointers, the left and the right, by 1. Now the triplets that we have are -1, 0, and 1, which add up to 0 again, and this becomes our next triplet that we want. Now as we learned before, we'll move our left and right pointer by 1, so the left pointer goes to over here and the right pointer goes over here. And now they have crossed each other and will encounter the same numbers that we have worked on before. So at this point we can stop because we have evaluated all the numbers that were there. So in this case, we are done with -1 and we'll move to the next -1. But we already worked on -1 and we found all the triplets that would result in a 0. So there's no point in working on -1 again. So we can just skip this -1 and move on to the next number, which is 0. Now we initialize the 2 pointers again, the left pointer and the right pointer, and we evaluate the sum, which is 0, 1, and 2, which adds up to 3. And because 3 is greater than 0, this means we need to find a smaller number, which would mean moving the right pointer towards left. But now left and right pointer point to the same index, so we can break this loop and stop searching for more pairs. So we couldn't find any triplets with 0. So moving on to the next index, it will be 1. We'll initialize our left and right pointer to the same index, which we cannot do. So we stop our loop again and move to the next number, which is 2. And then we initialize our left pointer, which is out of bounds, and the right pointer towards the end, which is not right anymore because we are out of bounds right here. So we can stop our iteration, and we found our 2 triplets, which are right here. So I want to discuss this case that we encountered where we skipped -1 just because we already evaluated this -1 right here. So let me just rewrite this. So we had -4 and -1, and let's say we had a couple more -1s, and then we had 0, 1, 2, and let's say 3. Now in this case, when we work on -1, we use the rest of the element and try to find sets of pairs such that they add up to 0. So in this case, that was -1, then another -1 and 2, and we had -1, 0, and 1. So once we found these pairs, they will always remain the same for -1. So if we encounter more -1 after working on a -1 already, we can just skip these because we'll just get the same results, and that will just give us the same triplets over and over again. So let's talk about another optimization. So let's say our input was -4, then -1, and then a bunch of -1s, then 0, 1, and 2. Now when we find the triplet for this -1, it will be this -1 and 2. And this is how our left pointer and right pointer will look like. But if you think about these two numbers, -1 and 2, they will always need another -1 such that the sum becomes 0. And as we increment our left pointer, we can see we encounter a -1 again and a -1 again, which always gives you the same triplet. So it might make more sense to keep moving our left pointer all the way towards right until we find another number which is not equal to the number that we've already found by our left pointer. In this case, left pointer was -1, which added up to 0 already. We just keep moving right towards 0 because now this is a different number than what we have seen before. And we can do something similar for the right pointer. So let's say we had -4, -1, 0, 1, 1, 1, 1, and 2. Then our triplets become -1, 0, and 1. Now in this case, for -1 and 0, the only way we can sum up with 0 is by encountering another 1, which we did right here. But as we move our right pointer more towards left, we see that we can skip these because they will all add up to 0 and they are not unique because we have already worked on -1, 0, and 1 as a triplet that add up as 0. So just like the left pointer, we can keep moving our right pointer towards left until we encounter another unique number, which will be 0 in this case. So these are some of the optimizations that we can do. So in summary, if we had -4, -1, -1, 0, 0, 1, 1, and 2, then our first optimization will be to skip the first number of the triplet that we have. Once we find all the pairs for a given number, like for -1, we know it's 0 and 1 and -1 and 2. Once you find all of these pairs that add up to 0, we don't have to work on -1 again because we have already worked on that number and we have found all the triplets that add up to 0. So we keep skipping the first element of a triplet if you have already tried to find all the triplets for it. Then the second optimization that we talked about was if we find a triplet, then we can keep moving our left pointer all the way forward until we find another unique number that wasn't pointed previously by this left pointer. Otherwise, we'll just end up with the same triplets over and over again. And the same logic goes with the right pointer. Once we find a triplet that adds up to 0, we can keep moving this right pointer towards left until we find another unique number which is not equal to the number pointed by the right pointer. Otherwise, we'll again end up with the same triplet. I hope this made sense to you, and if not, I'll recommend watching this a couple of times and doing your own dry runs and taking up examples. It took me some time to figure out the solution and to really grasp why these optimizations work. So yeah, I highly recommend that you spend time on your own and just work through some random examples, and I'm sure this will make more sense to you. So let's take a look at the pseudocode summarizing everything that we need to do. Okay, so here's the pseudocode for the optimal solution that we just discussed. I know it looks chunky, but trust me, it's pretty straightforward. So we start by taking the input, which is our nums array, and then we sort it. Then we start a loop from 0 to the length of nums. And if the current element is greater than 0, then we are done, as there's no way we can find two more elements that will add up to 0, because those two elements will be greater than 0 as well. And we cannot add three numbers that are greater than 0 to 0. Then if our current number is the same as the previous number, then we skip it, because we found the right pairs for the current number already. So if we try to find more pairs, then we'll just end up with the same triplets again. So we just ignore our current element if it's the same as the previous one. Otherwise, we initialize a left pointer, which starts from our next element, so it's loop plus 1, and then we have a right pointer, which starts from the end of the array, which is nums.length minus 1. Now we start a while loop, which keeps going until left pointer is smaller than right pointer. And then we sum up the current element, the number pointed by left pointer, and the right pointer. Now if sum is smaller than 0, then we need a larger number, and the only way to get it is by increasing our left pointer by 1. But if our sum is greater than 0, that means we need something smaller, and we can do that by decrementing our right pointer by 1. Otherwise, if sum is 0, then this is the triplet that we have been looking for. And then we optimize our algorithm by skipping the numbers pointed by left pointer if the number pointed by left pointer is the same as the previous left element. And we do similarly for the right pointer as well. And once we're done with the for loop, we just return all the unique triplets that we just found. Okay, so let's code this solution, and hopefully the algorithm will make much more sense then. Okay, so let's work on an optimal solution. Let me get rid of this brute force right here. So let's add our base case. Let's say if nums was empty, that is, its length was 0, then we can just return an empty set of result. Otherwise, as you brainstorm, the first thing we should do is sort this array, which we can do by this. And now let's run a loop. Let's use I as our loop variable. and run it all the way towards the end of the array and then increment it by 1. Then let's add our first base case that we had. If the current number that we are working on, that is the first number of the triplet, if it's greater than 0, then we cannot find any pair that will add up to 0. So we can simply break out of our loop and return whatever we have. Otherwise, let's initialize a left pointer, which will point to the next index, and then we'll initialize a right pointer that will point towards the end of the array. Now let's run a while loop until our left pointer is smaller than the right pointer. Otherwise, they'll just cross each other and start working on the same numbers again that we have already worked on. Then let's try to add up the sum. In this case, we'll assign it to long in case there's an overflow, which will be the first number in the triplet pointed by the loop I, then the second number in the triplet that will be pointed by the left pointer, and then the third triplet, which is pointed by the right pointer. Now, if sum is 0 in this case, then this is the triplet that we need, and we'll come back to it. Otherwise, if sum is greater than 0, then we'll do something else. Else, if sum is smaller than 0, then we'll do something else. Now, as we discussed, if sum is greater than 0, then we need a smaller number. And we can get a smaller number by decrementing our right pointer by 1. Otherwise, if sum is smaller than 0, then we need a larger number, which we can get by incrementing our left pointer by 1. And IntelliJ is suggesting here that you don't really need this if condition because this will always be true, which makes sense. So we can unwrap this. Okay, so now let's tackle what will we do when sum is actually 0. In this case, let's first add it to a result, which will be arrays as list, and then the 3 numbers in our triplet, which will be num_i, num by left pointer, and num by the right pointer. And let's see if this works. I suppose it's stuck in an infinite loop right now because we forgot to increment or decrement our left pointer. So let's increment our left pointer by 1 and decrement the left pointer by 1. And let's try to run this code now. Okay, it seems like this works, but we still need to add our optimizations where we skip the numbers that we've already seen for left pointer, right pointer, and our loop I. So let's start by adding that logic for our left pointer. So we need some way to track what was the last left number that we have seen. So let's call it last left and store the last left that we have seen, which is pointed by the left pointer. And let's do the same thing for the right. In this case, let's call it last right and store the number pointed by the right pointer. Now we can add another while loop in here. While the left pointer is smaller than the right pointer, which is the base logic that we need so that the pointers don't cross each other, and the left number that we have seen is still the same as the current number that's pointed by the left pointer, then we just increment our left pointer and keep skipping those numbers. And we'll do exactly the same thing for the right pointer. So copying this, adding the base case so the pointers don't cross each other, and as long as our last right is same as the right number which is pointed by the right pointer, we just keep skipping it. So in this case, we do right pointer, but we decrement it because right pointer moves towards left. Let's make sure this still works. Let's run this. Okay, and looks like there's some bug right here. Oh, and I guess that's because we didn't remove this left pointer. So there was an extra increment for the left pointer. Let's remove this and run this again. Okay, now everything works fine. And that's how you get bugs in the code sometimes. So we have worked on left pointer and the right pointer so that it skips the same numbers. And now let's do the same thing for our number I. So for this, we can add a base case. If I is greater than 0, and if the current number pointed by I is the same as the previous number that we've encountered, which is represented by I-1, then we can just skip this whole loop and we move to the next iteration. And because we are doing I-1, this I greater than 0 condition is necessary. Otherwise, we'll try to access the -1 index, which will be out of bounds. Okay, let's run this now. This is still correct answer. And another optimization that we can add here is run I from 0 to num length -2, because the last 2 elements are again taken care of by the left pointer and the right pointer. So let's run this again and we can see it's still the correct answer. Okay, so let's copy this over to LeetCode and see how well does this one perform. So copying this, going to LeetCode, replacing our current program with this new optimized code and running the base case, which was successful. And now submitting this. Okay, and it looks like LeetCode likes our solution. Okay, that's all I had for this video. I know that this 3-sum problem was slightly complicated, but I hope that you enjoyed brainstorming on the brute force and the optimal solution. And if this video helped you, please don't forget to like and subscribe to my channel, as I'll keep making more and more interview videos. Also, don't forget to follow me on Twitter, or buy me a coffee, or follow me on so many other platforms where I'm trying to build a presence and reach out to larger audience. I'm working on more LeetCode videos, so they'll be coming out soon. Thank you so much for joining in. Have a great day, everyone.